potential at a point due to a point mass. Let us suppose here is a point mass, say at the point O. This is the point mass M is kept, and we want to find potential at a point, say here at the point, say P, at a distance r from O. Now we know that potential at P is what? The work done to bring a unit mass from infinite up to the point P. Now let us join OP and extend it up to say any point Pn. Now divide this point Ppn by say P1, P2, P3, Pn minus 1, so that P1 is at a distance r1 from O, P2 is at a distance r2 from O, P3 is at a distance r3 from O, Pn minus 1 is at a distance Rn minus 1, and Pn is at a distance Rn from O. Now suppose here we imagine a unit mass, say 1 kg mass here. Now the force at P due to the point mass M at O, force at P will be G mass into, this is the unit mass, into 1 by square of distance. Similarly, if we consider the point mass at the point P1, we find that force at P1 is G M square of distance r1 square. Now here, by comparing these two force at P and P1, we find that the force differs by inverse square distances. So we can say that the average force between P and P1 can be obtained by taking the geometric mean of these two forces. That is, force between P and P1 is geometric mean of these two forces, Gm by r square into Gm by r1 square. So that is equal to G M by r1. So the work done to displace this unit mass from P to P1, we can say work done to displace the point mass from P to P1 is equal to this force Gm by r1 into the displacement. This PP1 distance is what? R1 minus R, R1 minus R, that is equal to Gm by 1 by R1 by R1, so 1 by R minus 1 by R1. Similarly, work done to displace the point mass from P1 to P2 can be obtained as Gm by 1 by R1 minus 1 by R2. Likewise, we can find out all the work done to displace the point mass from this unit mass from P to P1, P1 to P2, P2 to P3, and Pn minus 1 to Pn, Pn minus 1 to Pn. This work done will be equal to G M 1 by Rn minus 1 minus 1 by Rn. Now work is a scalar quantity, so if we add all these individual work, then we can get the total work done to displace the unit mass from P to Pn. So work done to displace it from P to Pn can be obtained by summing up all this. So 1 by R1, 1 by R1 cancel out, R2 will cancel out the next term, similarly Rn minus 1 will cancel out. So this becomes G m by 1 by r minus 1 by Rn. So this is the work done to displace unit mass from P to Pn. This work is Gm 1 by r minus 1 by Rn. Now this point Pn was taken arbitrarily. It can be taken at infinity, means beyond the gravitational field of this point mass m. So if we take this point Pn at infinity, see this at infinity, then Rn will be infinite. So this will be infinite. 1 by infinity is 0. So the work done to displace the unit mass from P to infinity will be Gm by r. So therefore, suppose this is the work done to displace from P to infinity. So similarly, if we bring a unit mass from infinity to P, this work will be done in favor of the attractive gravitational force. So we can take the negative sign of it, and we can find out the work done to bring the unit mass from infinity to P. So therefore the work done to bring the unit mass from infinity to P equal to minus Gm by r. This is gravitational potential at the point P. So thus gravitational potential is minus G is universal gravitational constant, m is the mass of this point mass, and r is the distance.